Okay, let's start today's class. Today we are going to start a new topic. It is 8086 interrupts. Okay, so let's first understand what is the requirement of interrupt and what is the difference between an interrupt and a polling. Okay, so when you have an 8086 or any processor for that matter, you will have certain external devices which are which are connected to it. Okay, there will be some external ports onto which some IO devices will be connected. Like for example, there could be a printer, there could be a keyboard, there could be a mouse, or within the hardware there could be some temperature sensor, or there could be some like a battery sensor which will give the condition of the battery to the microprocessors, right? So all these things, and there are several inputs which will come to the microprocessor. So one way to keep monitoring is known as polling, in which the microprocessor at a periodic interval stops the microprocessor also could be running some program, right? It could be the operating system or some memory transfer information, or you could be playing a movie or whatever it is. It could be doing some program, right? In between, it has to keep checking whether one of these inputs whether they are giving some input or not. Like, have you pressed a pause button if you are playing a video, or if something is being given from the mouse, from the keyboard. So something known as polling it can do. That is, it can stop the program which it is running, right, at regular intervals, and keep checking all the input ports. And then again, if there is some input, and you take action accordingly. Otherwise, you come back to the original. So this is known as polling. So this is a total wastage of time, if you see, right? Unnecessarily you will have to keep stopping. If there is no input at all coming, still you will have to keep stopping and keep searching for if there is an input from all the IO ports, right? So this is not generally resorted to. So we have something known as interrupts. Okay, interrupts is, it will continue to do a program whichever it is assigned. Okay, only thing is, whenever an input device wants to send a message, it will interrupt the program which it is running. So the microprocessor has got certain interrupt pins, or there are certain soft interrupts. So whenever an IO port wants to tell something to the microprocessor, okay, it will send an interrupt signal, and only on receipt of interrupt signal, the current program which is being run, it will be paused for some time. It will go and respond to the interrupt and come back to the original program. So this is known as an interrupt signal. Okay. So if you see, there are several kinds of interrupts in 8086. Okay, first there are something known as software interrupts. Okay, so when you write a program, okay, you can write in between an interrupt. Okay, and then you can follow it up with a number. Okay, this number can be from 0 to 256. Okay, so there are 256 types of interrupts, right? So 256 numbers means it's an single byte information. So you can write 256 types of it's an 8-bit number, right? So total from 00 to FF. So there are total 256 types of various interrupts. Okay, there are total available in 8086. Okay, out of which there are around first 5 which are they're fixed. Okay, that is done by Intel itself. In fact, from 5 to 31 also, although that they are also kind of the first 5 are very critical. It is fixed by interrupt. Some from 5 to 32 also. Most of the processors, it is pre-programmed by the manufacturer, whosoever is making the motherboard. Okay, so that is also fixed. And then from 32 to 256, you can program it. Okay, what kind of interrupt you want. Okay, so what is interrupt? It is just, you say interrupt 1. So it will go. It is a procedure which will be called for, and it will execute that procedure. Whatever you have written in that procedure, procedure we know, right? It will do an and it will go do a near jump or a far jump and call for that procedure and execute that instructions which is written in that procedure, and it will return back to the original program. So similarly there are 256 types of interrupts, and each of them is a small program in itself. Okay, it is set of instructions which the microprocessor has to do, right? Then there are some thing known as hardware interrupts. Okay, so the hardware interrupts also, this software interrupts is triggered by within the software when we write int followed by that number. So one among the 256 is called for. Hardware interrupts also, the way it is triggered is through by giving the signals to the pins, but again it will be one of the interrupts which is already all these 256 have to be programmed initially itself. Okay, and from the software interrupts you can call for one among the 256. Similarly, in the hardware also, one of these 256 will be triggered. Okay, only difference is this is triggered through a software instruction, whereas this is triggered through hardware signal. Okay, that is the only difference, but finally one among these 256 have to be selected. Okay, so there are two types of hardware interrupts. Okay, one is maskable interrupts. That means we know what is a maskable interrupt that we studied in the when we studied the flag. So there is a flag, right? In the flag register there is one flag which is known as interrupt. If that interrupt flag is set to 0, then even if this hardware signal is sent, okay, the microprocessor will not implement implement this interrupt, will not service this interrupt. Okay, you can call that way. Now, whereas non-maskable interrupt, okay, in this whenever this non-maskable interrupt is triggered, okay, so it is not dependent on the flag register, the setting of the interrupt bit in the flag register. So it will, whenever this is the highest priority interrupt, non-maskable interrupt, whenever this interrupt signal is given to the 8086 microprocessor, it will just finish whatever instruction it is doing and then execute the non-maskable interrupt. So this is one of the most important interrupt. So let's see how it is triggered. So this is an 8086 processor. So there is a pin known as NMI. Okay, so whenever a non-maskable interrupt is to be started, so this on this pin you have an NMI pin number 17, into which a 5-volt signal is given by the hardware. Okay, so once this 5-volt signal is given here, the microprocessor, whatever program it's doing currently, okay, it will store the IP and the CS values into the stack register, and then it will start executing this program, this NMI program, and then once it is done, that interrupt is serviced, it will come back to the original program. So generally, like if you have, for example, in the hardware you have low battery signal coming, right? There will be few sensors. Okay, it will be low battery or high temperature. Okay, these are some of the sensors which are there in the motherboard. So if the motherboard detects, okay, there is some low battery issue, high temperature issue, or there is a problem with the RAM and all, some hardware issues, critical issues, okay, then the motherboard will send a signal to the processor, okay, through this, by giving a 5-volt in this pin. Okay, then the 8086 will go to the corresponding interrupt procedure subroutine, and then it will run that and accordingly do some action. Okay, it could be like giving a message to the user that the bat is going to shut off within another 5 minutes, or it could just go into a standby mode or things like that. So whatever is written there, so that would happen. Okay. Similarly, there could be some maskable interrupts. Okay, so this is given by the various IO devices which are connected, like from the printer or the mouse or the keypad, and also whenever we when we press a keyboard or a mouse, so that will produce an interrupt signal to 8086. Okay, so once this interrupt is there, then accordingly the interrupt subroutine, and we'll also have to tell the microprocessor what kind of interrupt we require, okay, when we are pressing the let me go to the next slide. Okay, this is a maskable interrupt, so we are going to give it in pin number 18. Okay, this pin is known as interrupt, and obviously for 8086 to start this to service this interrupt, this flag has to be set one interrupt flag, right? This is the flag register. If this flag is set to 0, and this is programmable, okay, by the user. If we set this to 0, then no interrupt, and it would not accept any interrupt. So once we tell when a maskable interrupt is telling the interrupt, okay, this 8086 also needs to be told to which interrupt it has to go from 0 to 256. Okay, that also needs to be told to the 8086. Whereas in the case of non-maskable interrupt, okay, it knows, okay, where to go, which interrupt it has to do. It is known to the 8086. So we'll see that, right? Okay. Now this is how things work when an
excuse me, sir.
Yeah.
So could you just go back 1 second?
Yeah.
So the previous slide.
Yeah. Tell me.
Yes, sir. So, sir, so I opened I opened the lecture slides from the third lecture where you had mentioned all the pins and their directions and all.
Oh, okay.
In that, it is given that interrupt is only interrupt only is towards is in and the NMI is in and out. So, what is the significance of NMI being both in and out pin?
NMI is shown as okay. Then there could be an error. NMI is also an input pin. Okay. These are interrupt pins. Both are in. Okay.
Yes, sir.
Okay, we need to give only the positive to trigger it for the reset. Okay. So now this is the sequence which happens whenever an IO port wants to do an interrupt. Okay, now we are talking about the hardware pins. Okay, these two pins, NMI and N. So in the case of interrupt, the interrupt signal goes high, right? And then there is an interrupt acknowledgement pin also in the 8086. Sorry, let me go back here. Where is the interrupt acknowledgement? Can we see? We learnt about one interrupt acknowledgement also, right? There is an interrupt acknowledgement pin. These are all pins here. Yeah, interrupt acknowledgement here, right? There is an interrupt acknowledgement pin also available. So the interrupt acknowledgement will go low initially, right, whenever there is an interrupt which is coming here. Okay, this will tell IO, okay, I have received your interrupt signal. You be ready to tell me now what is the interrupt which I have to service. Okay, and then the microprocessor sends in the next clock cycle one more interrupt, and this is it is all negative edge triggered. In the next negative edge when it's going down, the interrupt acknowledgement, now the microprocessor, this is meant to tell the IO device, okay, now you tell me what is the kind of interrupt you want to do out of the 256, which is the one I need to run. Okay, now the IO device, okay, is going to place the tell the microprocessor among the 256 what is the IO which it wants the 8086 to service. So it will put that 1 byte of information here on the address line from 0, not on the address line, on the data line. Okay, because this multiplex. So on the data line, the IO will put the byte information about which kind of interrupt it wants. Okay, so and then accordingly 8086 will now go and execute that particular interrupt. Okay, yeah, is it okay? Okay, first the interrupt signal goes high, right? Then telling the 8086 requesting the 8086, okay, I want an interrupt. The 8086 will first check whether the mask if the interrupt flag is high. If it is high, it will send an it will complete the interrupt which it's doing, right? The instruction which it is presently doing. It will not stop halfway through. It will just complete that instruction and then send an interrupt acknowledgement signal. Okay, and then this is just to tell the IO device, okay, I have received your interrupt. Be ready to give me the data. Okay, data is a one byte data which will indicate which is the interrupt I have to do, right? Okay, again the interrupt will go down in the next clock cycle. Then the interrupt data is placed here. Okay, the 8-bit data is placed here. So now the microprocessor knows what kind of interrupt it has to do. So once it completes that interrupt subroutine, okay, it will come back to the original program. Okay, so that is how it is done. Whereas for non-maskable interrupt, okay, the signal will go high and it has to just remain high for 2 or 3 clock cycles. Then it will automatically go and execute what it has to do, because it is known once the now for NMI it is known what kind of interrupt it has to do. Okay, so the microprocessor will know where to go and where to call, which interrupt it has to be called, because that is fixed. That we will see now. Okay, now this is where
So could you once again explain the INTA bar? Why does it go up and down? It goes down and then up and again down.
There it actually 2 clock cycles are required. In the first clock cycle, because there will be many IO devices, right? Which are connected, though they might be giving signals in parallel also. So we'll see how it is how the priority is given to various in when we study the interrupts further. But what we see is once the interrupt is given, so the IO devices they'll keep waiting for first the acknowledgement. Okay, once it receives an acknowledgement, then there is an interrupt controller in between. We'll see that. So what the interrupt controller what it does is it receives lot of it is connected to various IOs. And it will so it places one interrupt whenever it receives an interrupt request from one of the IOs. It will place an interrupt request to the microprocessor, and once the microprocessor tells, okay, I am ready to receive the interrupt signal, then it depending on from which input IO port it has received the interrupt, it will synthesize the type of interrupt which is to be done, and it will be kept ready. And in the next clock cycle, that interrupt address, okay, out of 256, which is the one which requires to be synthesized, which is to be run, so that is placed onto the address bus here. So that is why there is a requirement of 2 clock cycles out here. First will just tell, okay, I am ready to accept the interrupt and keep the interrupt data ready. Okay, this data is nothing but to tell the microprocessor which interrupt does it want to execute. Okay, is it okay?
Sir, and why is there a small delay between INTA bar going low and the address line being latched with interrupt value?
No, that is because of the physical issues. Okay, because the interrupt controller will take a certain time for it to get, but it is triggered by this. Okay, the moment the low signal comes here, the interrupt controller will there will be few picoseconds or nanoseconds delay. Okay, that will place the data,
Yes, sir.
data here, right? Okay, so now if you see now where are these 256 interrupts? Okay, how it is organized. So there is something known as vector table. Okay, the vector table starts with the in the first 1 kilobyte of information of the memory is reserved for vector table. Okay, first if you see the address CS is 000 here, and from 000 to this value 03F. So this 1 kilobyte of information, okay, 256 byte, it is 1 kilobyte is reserved for the vector table. Okay, now what is a vector table? Now for interrupt 0, okay, the 4 bytes are reserved here. Okay, here 4 bytes of this memory location is reserved here. Okay, the first 2 bytes will have the IP address, and the next 2 bytes will have the address of the CS register. Okay, so these IP address 2 bytes and these two they will together indicate one address, okay, one physical address in which that interrupt starts. Okay, so when I say, if I write, say suppose if I say interrupt 0, if I write a command, what will do, the microprocessor will come here and look for the IP and CS. Okay, so and then it will calculate the physical address whatever is there, and it will go to that physical address and execute that instruction, that set of instructions which is written there. It will execute the procedure which is written there. It will jump to that procedure, complete it, and then come back to the main program. So if you see this table only contains, okay, the IP and CS of all the 256 interrupts. Okay, so type 0 interrupt, type 1, it will go up to type 256. Okay, and each of these in this vector table it is 4 byte, right, because IP is a 16-bit number, and and the CS is also 16-bit. Okay, we need to know the address of IP and CS. Both are 16 bits, right? So there are 2 bytes of information available, 2 bytes of information available in each row, right? So if you see 256 into 4, that is 1 kilobyte. So this entire memory is 1 kilobyte of information, and each of these interrupts, whenever we write an interrupt, or it could be a hardware interrupt also. Okay, once whichever number we specify, the microprocessor is going to fetch the IP address and the CS address from this vector table. Is the concept of vector table clear to all of you? Is there any doubt? I can repeat it, and okay, if you have any doubt,
So
yeah.
basically, a vector table stores all the address values of different programs that have been written in different parts of the code segment, right?
Correct. So all the 256 different interrupts, okay, interrupt programs, they're all small programs in itself. They're all procedures. In fact, they are written in different parts of the code segment. When you are writing a like first few will be written by the Intel itself. Okay, there will be few written by the hardware manufacturer, right? And then there are a few things which is available for you to write. So whenever you write a program, you will fill those. So whenever you write a procedure, automatically the microprocessor will keep updating this table. Okay, so all the information where these interrupts have been written, that will be available in this vector table. So whenever an interrupt is triggered, it will look for the corresponding IP and CS from this table. Okay, it will pick up these values, and then it will come. Okay, now let me tell. Yeah, I am coming, Ruben. I am coming to these issues. Type 0. What is type? These 5 interrupts is done by the Intel itself. So this never changes. Okay, these interrupts are never. Okay, type 0 interrupt is whenever the microprocessor encounters and divide by 0 instruction. Okay, for some reason you might have written a complex in equation. For some reason, say some variable in the denominator becomes 0. Okay, so it will keep the divider module will go into an infinite loop. To prevent that, whenever it encounters a divide by 0, this interrupt will be triggered automatically by the system itself. Okay, so we don't write int 0 and all. This is automatically triggered. This interrupt signal will be automatically triggered as and when a divide by 0 is encountered. Okay, these 5 are pre-programmed by the Intel itself. Okay, we can't change any of these. Okay, we don't have access to this. Okay, Similarly, type 1 is for debugging. Debugging is whenever there is some problem with the hardware or some instruction, and this is again by the manufacturer only. When the your microprocessor runs into your PC runs into a problem, it is during debugging of the problem with the microprocessor. This is done in a single step, like each step will be executed and it will stop once when you give an instruction. So this is also not available with the user. Okay, this I said is again not available with the user. So whenever an NMI interrupt comes, okay, I told the address need not be told to the microprocessor because this NMI address is known. Okay, it is the type 2 interrupt. Okay, so the microprocessor, whenever the NMI signal goes high, the microprocessor will automatically come and it will know, okay, this is the instruction which requires to be interrupt, and type 2 has to be initiated. Okay, type 2 interrupt. So this value of that NMI program, wherever it is written, the IP starts here and the CS address starts here. Okay, so automatically this is triggered, this particular subroutine. Similarly, the next one is reserved for a single byte instruction, reserved for int single byte instruction. Okay, this is also not available for the user. This is also used for debugging, and this is int overflow. So whenever there is an overflow happening with it's not exactly divide by 0, but still it is going beyond the computing capability of the when there is an overflow. That is like if we use an IEEE format, so it can handle fairly large range of bits. Okay, like it is not done binary, which we didn't discuss. It is actually IEEE format. It is used where you have an mantissa and so it is in exponential form, the bits, so that you can represent large number of bits even in 16 bit. Okay, it is not 2 to the power of 16 is not the maximum number of bit which the processor can use. Out of the 16 bits, if you see, few bits will be only the mantissa, and the rest will be the exponential function also. So in fact it can handle a large number, but still in some cases if there is an overflow, then this program will be triggered and you will get a warning accordingly. Okay, so then there are all these are few of them are again programmed by the hardware guy, and then you will have a few left for your software interrupts also, which you can program yourself also. So this is like if int O is triggered, if you try to move BL00 and AL some value and divide by BL, okay, you will get an error message like this, like divide error overflow. Okay, you will get so this kind of error. So this error, where does this message come from? Because this is written in the int O, right, int 0. So this program is written in the int O, so that has got triggered, and that is why you are getting an display like this. Okay, that this is in int 0 is executed, and that is the reason this error message has come up. Okay, this you can try it out yourself also.
So it is possible to manually change any interrupt?
No, the
As
first,
in we can.
the first few cannot be. I am just coming to that. Okay. See, the first 00 to 04 interrupts, they are fixed operations, and hence they are called dedicated interrupts. You can't do anything about that. Okay, so these are the interrupts which you can't change. Okay, the first is if you see these are the first 5, right? Divide by 0 you can't do anything, and reserved for single step, this you can't do. Reserved for NMI, because this is an hardware related. Okay, whenever there is an issue with hardware, okay, it could be a temperature or a battery issue or something. So NMI will be triggered. So within the NMI, again there could be several conditions, right? When in the NMI, once it is triggered, it might go to NMI, and then it might say, okay, read temperature, read battery. So when the NMI goes high, it only comes to know that first the microprocessor said that there is some issue, some hardware issue, and what is the issue, that is not known. So it might go to that NMI and subroutine. Within the subroutine, you might take several inputs now: read temperature, read the condition of the RAM, read the condition of the like battery, and then accordingly, if there is some problem, it might tell, okay, now if the battery is high, okay, give a warning that it is going to, battery is low and it is going to shut in 30 minutes. Okay, or it could if the temperature is high, it can just tell, give a warning that the temperature is high and I am going into standby mode. So those kind of the program might be elaborated in the NMI procedure. Okay. So these and int overflow. So whenever there is an int overflow, it might tell, okay, and the data is there is an overflow condition, and it's an data could be erroneous. Okay, so these kind of warnings it can. So these we cannot change. Okay. And after that also, from 5 to 31 also, they are actually preserved for higher processors. So there is 8086 doesn't use these interrupts. Okay, from 32 to 255 you can program. Okay, you can program these interrupts. Okay, so generally within these also, some of them are pre-programmed also, standard ones. There are several standard ones like int 21, which we did in the lab. I explained yesterday. Int 21, okay, is an interrupt table, in which within int 21 we have to initially tell what is the value of the AH. So once we do int 21, it will go to a particular subroutine, and then the first thing it will do is it will read the value of AH, and depending on various values of the AH, it will do one of the functions which is written there, like reading from an input and putting an display, give the same display out, or read the date and time of the system and display those things. So those kind of this is pre-programmed. So you can also program, and you can also write interrupt programs. So but these are all programmable, right? So these are what yeah, sir, int 0 into 10 enables video display, as we can manipulate the display screen. Is that still part of Intel, or does it belong to other processors? Int 0 into 10 means what does it mean? Can you switch on your mic and speak? That would be better.
I think so. There's interrupt called the of type 10. So int 10h. So basically, if you do that, you can based on the value given in the other registers like or the CX register, then you can do different operations. Like you can you can paint certain pixels on the screen, or like that. So do those belong to Intel, or they belong to other processors?
No, I think it may not be applicable to 8086. Okay, it might be for 80386 or something and higher version, because if you see 5 to 31, it is for higher processors. So 5 to 31, obviously it is Intel only, but not 8086, higher than 8086 maybe.
Because they're actually DOS interrupts for the MS-DOS operating system.
Yeah. So I think the book says so. We'll have to try. We can try it out in 8086 and try if it emulator. Okay. Or we'll have to refer to the 8086 in a manual and see whether these interrupts are also. But no, this is there in the book. It's written. It's not preserved for higher processors, and I think this is not applicable for 8086. Okay. So. Now how does this interrupt cycle runs? Okay, so whenever an interrupt command is given to the processor, or there is a hardware interrupt, what it does is, first it is going to push the flag register contents into the stack. Okay, and then it will clear the interrupt flag. Okay, because now it is already executing one interrupt. Okay, so the interrupt flag will become 0 till this instruction, because you can't have two parallel interrupts running, right? So whenever I am putting this the contents of the flag register, I am going to push it into the stack, and then I am going to clear the IF, and also I am going to trap. Okay, trap is also stepwise, right? We said it is in a stepwise function. Whenever we want to debug the problem with, then the track flag is set to 1. So these two flag is also set to 0, because now we can't service these two once the one interrupt is being serviced. So this will get to 0. Then the contents of the CS and IP is also pushed into the into the stack register. Okay, and now it says load CS and IP. Okay, where does it load this CS and IP? From the vector table. Okay, from the vector table, the CS and IP, whichever is the interrupt, corresponding to that, the CS and IP will be loaded. Now the new CS and IP will be loaded here, and accordingly the interrupt subroutine will run. Okay, in the end of the interrupt subroutine, you will have I return. Okay, once it I return, it will come back. So now if you see the IP and the CS registers, and okay, it will go the previous whatever it was stored in the stack register, that comes in, and then you are going to pop the flags also. All the flags which was stored in the CS register, in the stack register, that will also be called back, and now the flag register also gets updated with the previous value, and it will continue with the main program now. Okay, is it okay? Okay, so now
So could you explain that part once again?
yeah, okay. Whenever there is an interrupt and a signal which is coming, and now the interrupt needs to be the main program is running out here. Whenever there is an interrupt signal, now what it does is it is going to push the contents of the flag register into the stack register. Okay, and then it is also going to clear the interrupt flag and the trap flag to 0 0, and then push the contents of the present, because there is a program running. Now I have been interrupted, so I'll service the interrupt, and later on I need to come back to the original program. So that is the reason I am going to push the contents of CS and IP also into the stack register. Okay, now once I have pushed that contents of CS into stack register, I will load an CS and IP corresponding to the looking from the vector table. Okay, if it is interrupt 2, then I'll go and see what is the CS and IP corresponding to interrupt 2 in the vector table. If it is interrupt say 35, then the corresponding CS and IP from the vector table, that will be loaded here. Okay, once it is the new CS and IP corresponding to the interrupt subroutine is loaded here, that program will start running. At the end of that program, you will have in the procedure you will write I return, right? So once you return I return, it will come back to the original program by popping up the IP and CS from the stack register. Excuse me. And also updating the flag register, which you have already pushed it in the stack register. So these two pop instructions will get back the IS and IP and CS, and also the flag register status, and it will run the main program again. Is it clear now?
Yes, sir.
Okay. So this is a soft interrupt. So just a second, my mobile is ringing. Let me put it off. Yeah, sorry for that. Okay, now this is how you write an interrupt program. While this might be your code which is running. In the code, you might, this is soft interrupts also are there, right? So within the code also you can write in between an int 09h. Okay, so it will call for that interrupt subroutine. So the interrupt subroutine is written starting from here. Okay, it is a procedure, right? So you have to name the name. Your name is to be given to the procedure, right? So this is procedure, and then the name is given. Like generally when we write when we call for a procedure, you give some name for the procedure, right? In this case the name is given like this, interrupt subroutine 09h. Okay, so this is the name of the subroutine which is given there, and then when you call 09H, automatically this will be written. And also when you write ISR 09H, the vector table will get updated automatically, that this the address in the code, this is the code which you are writing. So whatever is the corresponding address of this memory location, that will be updated in the vector table also. So once you write the procedure, in the end there will be a return and then end procedure, right? So then it will automatically go back to the so this is how in the within the code you can call for an soft interrupt also, and this is how you write an interrupt program. Okay, anywhere in the code segment you can write, you just have to give a name out here, and the vector table gets accordingly updated. Okay, so this is the but this is interrupt is nothing but a procedure, right? It is just a procedure. Okay, here whatever is the instruction which you need to with the 8086 has to do on calling this interrupt, that will be written within the procedure. Okay, so I think with this we have come to end of interrupt lecture, but then let me just few things were left out from the previous lecture, so let me just cover that. There is something known as a bus cycle. So there are three types of cycle. There is something known as instruction cycle, machine cycle, and T states. Okay. So machine cycle, this is a concept which is not really applicable to 8086. Earlier processors which used to have very simple instructions, okay, those it is applicable to that. And the machine cycle consists of 4 steps. Okay, fetch. Okay, the first one is fetch the data, decode, fetch the instruction, decode the instruction, execute the instruction, and store the result. Okay, so this is these 4 steps together are known as a machine cycle, right? So it was it consists of 4 different operations. Then now the 8086 processor, okay, it can have complex instructions, right? It can handle. So it will require more than one machine cycles to perform. This is just a machine cycle is only 4 different things, but if you see instruction cycle is the complete time taken to complete one full instruction. So that could be complex, like it could read an instruction from a memory, decode the instruction as per the opcode, find the address operand, and retrieve an operand, perform the desired operation, find the address of the destination memory, store. So like for example, if you have written move AX within a square bracket and a BX, okay, now what it is, it has got several instructions within itself, right? It's a complex processor now. So first of all, the contents of the BX register, that is to be taken, then the address which is being pointed out by BX, and that needs to be the information is to be taken from there. Or if you write BX plus BX plus 10 or something, right, then the contents of the BX is to be taken, then and 10 is to be added to that, right? So and then that whatever is the result, the physical address is to be computed accordingly, and then the data requires to be taken from there, and then it needs to be stored. So if you see, an instruction cycle means the time taken for one full instruction of 8086. Okay, since it might have many up to 4 machine cycles also, right? It could have in the instruction cycle. It is a complete time taken for execution of one particular instruction. Okay, and the time taken will be different for different instructions, right? Some instructions will be small, some instructions will take a large amount of time, right? Okay, these are just definition you need to know.
So could you explain the find the address of operand and retrieve the operand part?
This one, right?
Yes,
Because
sir.
like I said, an example, BX plus you write BX plus SI, or you write SI plus 1, right, within square brackets, right, BX plus 10, right? Now you have to first compute that physical address, right, because it is not directly giving you the address of that physical memory location or something. So you're finding the address means you're computing that physical address, right, and then you are moving that address into the whatever is the temporary storage, and then doing desired operation. Is it okay?
Yes, sir.
Okay. So this is like you have since the 8086 can handle complex instructions, it is not pure machine cycle, it's an instruction cycle. Okay. And then you have something known as clock cycle also. These are the clocks, okay, single clocks. So this is one particular, this is known as the clock cycle, 1 clock pulse, 2 clock pulse, 3 clock pulse. So we have seen for read and write operation, without any wait it requires 4 clock cycles, and with wait depends on, if it's a slow memory you can have more than 4 operations also, 4 clock cycles also. So that is known as clock cycle, how many clock cycle per instruction. So reading into the memory or writing into the memory will take 4 clock cycles. Other instructions we will see subsequently when we see in the other few more instructions also, how many clock cycles they take, that we will see later on. But we have till now read about the memory read and write operations, which will take 4 clock cycles. Okay, that is known as the clock cycle. Okay. So again, Roman, you had a doubt last time, right, on this. So let me, you can connect RAM and ROM also. Generally, this is the case with how practically most of the 8086 motherboards, you will have RAM and ROM also. Why ROM? Because certain programs need to be like your ISR, like we said, some of them are pre-programmed by the manufacturer itself, right? There will be a lot of programs which the 8086 the booting sequence and things will be programmed and put into the ROM. You that will also be there, because with switching of power supply, if 8086 will not have any program, it is difficult to initiate it at all. And okay, excuse me. So some of the so you will have a ROM which is generally pre-programmed, and it will be available on the motherboard, and then you will have a RAM where you can do your programming. Okay, so in this the memories, so I am giving just an example where it's an easy way. If you have if you split the memory into 2 equal halves, 1 half for RAM and 1 for ROM, it's not necessarily you have to do like this, but I am just giving you one of the possibilities of splitting it like this. So in this case I have split it into 2 equal ROMs and ROMs. Okay. So the only difference now, for certain instructions, for the first half of the in an address, I want to select the RAM, and for the next half I want to select the ROM. Okay, so what I do is, again this has to be even odd, even odd. Okay, so instead of selecting giving a line A19, okay, that is the most significant bit. Okay, if it is 0, I can say, and I can give that also into a chip select logic, and then select these ROMs, and if it is A19 is equal to 1, I can select these chips. So this will become the ROM can be selected. So if you see the 1 MB memory which I have, so if you are going to put an address onto the address bus from 0 to 500 KB, right? So A19 will be 0, so this RAM will be selected in this case. Okay, so and if you see from A1 to A18 is the data which will come here. So because this is only now 256 bits over there, right, in parallel KB. So, so the number 1 bit will lesser will come here, whereas the most significant bit can be used to select this RAM, or it can be used to select this ROM. So this is one way of organizing your memory. Is it clear?
So at the end, to select either one of the block of 256 KB,
Yeah.
only 18 bits will be sent, right? Because A19 will decide whether it's RAM or ROM, and A0 will decide whether it's even or odd back.
Yeah, correct. A0 will A0 along with BHE will decide.
Yes, sir.
Yeah.
So only 18 bits will be sent, and
Yeah.
that will determine the.
Yeah. Yeah. So A19 will essentially will be used to select whether it is a RAM or a ROM. So you can do that, right? So if you want to don't have to split it into exactly half, then accordingly that you can do that, and only thing is your chip select will be slightly complex. So you will have to accordingly, if you specify, okay, I want to give only some part of the RAM. So for those memory addresses, the ROM, accordingly you will have to create a logic so that the ROM gets selected for those memory addresses, right? So accordingly you can do that. So this is also a way where this actually practically which is done. Okay, although textbooks they don't show this figure, but in all practical motherboards, including the one which we have in the lab, this is how it is done. Okay, is it okay? So I think that's all
Yes.
for today. We'll stop it here. If there are any doubts, further doubts, you can ask me now. Okay, if there is none, okay, thanks a lot. So we'll stop it here for today.